Alright, so hey guys, right now we'll be doing the tutorial questions on the lecture that we just did just now. So if you forgot what the lecture was about, it was about the power of a point with respect to a circle. Alright, so for this question, basically what you have to do is draw everything first as per usual. So let's just do that. Let me just read it again. What it's saying is that always the circumcenter of convex quadrilateral ABCD. So let's just try to draw something first. It might work, it might not work. We don't know. So let's just try. Convex quadrilateral ABCD. Let's just try something like this. B, C. So A, B, C, D. And then we're gonna draw a circle around it. Hopefully this fits. Yeah, kind of. Okay. So let's just eyeball the center, which is about here. Let's call this O. Okay, now next statement. AC and BD intersect at E. AC and BD intersect at E. If P is an interior point of quadrilateral ABCD such that okay, so let's just call this P such that PAB plus PCB. Okay, so we have to connect like this. PAB plus PCB. Ouch, wait, something hurt me. Okay, PAB plus PCB equals PBC. So we have to connect, that's PBC plus PDC equals 90 degrees. Okay, prove that OPE are collinear. So the reason why I put P here, although they say that it can be any other point, is because we want OPE to be collinear. We work with the end goal in mind. We want to prove that OPE, they are collinear like this. Okay, so what can we do? Let us consider, okay, let's just call this blue one. We have this blue circle already. Let's draw more circles. So we can draw a circle around APC. Okay, so APC gets a circle too. Okay. This is the circle of APC, that triangle, and then we have another circle which is around AP BPD, I mean. So BPD, there's also a circle also. Let's just, I'm reusing the color red because it's a very nice color to use to draw things because it's very obvious. Okay, so let's make it slightly bigger, and oops, I think this shall do. Okay, although in competition you don't need to draw the circles to absolute scale, but yeah. So if you notice, very obviously, the radical axis between the blue circle and the green circle is the line AC, and the radical axis between the blue circle and the red circle is the line BD. So what I'm saying is, this is the radical axis between the blue and the red, and this is the radical axis between the green and the blue. So since point E, if you realize, is both on this radical axis and this radical axis, what does that mean? That means what does that mean? That means power of point E to blue equals to red. Okay, since it lies on the radical axis of BD, and also power of point E to blue equals to green, because it also lies on AC. So now you kind of have the slight tingly feeling that E is the radical center of all three circles. What you have to do now is you have to prove that power of point E to the green and the red is the same, and then E will be concluded as the radical center, which will be useful. So one property that I can use is that in cyclic chord, now for example, we're taking the cyclic chord A, B, C, D. It's just a rule that AE times EC equals DE times EB. Okay, so what does that mean? This side is power of point point E with respect to the green circle. Okay, and this side is power of E with respect to the red circle. So the power of this immediately concludes power of point E to green equals to red. I'm not writing it in full, but you get what I mean, right? So now with these three conclusions, what you can conclude is E is radical center. Okay, so since E is the radical center, E lies on radical axis of the red and the green circles. Okay, since E is the radical center, so it must lie on the radical axis between the green and the red circle. So the radical axis is this point, is this line, which is the intersection. Basically you draw the line through the two intersections of the green and the red circle. So let's call this X, and the other intersection is P. So E lies on XP. That means E lies on XP, this line, That means E and P are collinear. Since E lies on XP, E and P must be collinear. Now we're almost done actually. We have proved the 2 points here to be collinear already. We just need to include O, since the question wants us to prove O, P and E are collinear. So what you want now is power of O with respect to red and green. Yeah, green and red is same. If power of O with respect to the green and the red is the same, that means this will go to O lies on radical axis, and it will be roped in to join this gang here, and hence O, E and P will be collinear. But this is what we want, which is not what we have now. Okay, we need to somehow prove that power of O with respect to green and red is the same. How are we going to do that? Well, let us take a look actually. Since okay, let's start off by looking at the angle APC. Okay, so angle APC would be equals to, so I'm saying this angle will be equals to the sum of all the angles in its complementary quad, right? So angle oh shit, don't know why it muted for a bit. Okay, so with this, definitely APC is equals to the sum of all three, right? Okay, so let's just use the things that they gave in the question. PAB and PCB, they are 90 degrees, so it's 90 degrees plus angle ABC. Okay, and this is ABC. Okay, this is also 90 degrees plus 180 minus, plus half, half angle AOC, plus angle at center is 2 times angle at circumference, right? So let's just dot this. Okay, so okay, now we have this. Let's just switch where we look to angle ACO. Angle ACO is, okay, since AOCR is like isosceles, this is 180 degrees minus angle AOC divide by 2, which is 90 degrees minus half AOC, which is very, very close to this if you realize. And in fact, you can transform it to that. This is just 180 degrees minus 90 degrees plus half angle AOC. Okay, which is 180 degrees minus angle ADC from what we have on top here. So now let's see what we have. ACO is 180 degrees minus ADC. So let's think a bit further. Okay. Oh wait, I just realized I did something wrong. It's actually APC. My handwriting killed me. So, sorry, my bad. ACO is 180 degrees minus APC. Okay, which is 180 degrees minus APC is just this angle and this angle, which is ACP and CAP. Okay, equal angle ACP plus angle CAP. So look what we have here. Angle ACO is equals to angle ACP plus angle CAP. Okay, anyway, angle ACO can be broken down into two angles, angle ACP and angle PCO. Okay, so just break it in the middle. So what we have here is angle ACP plus angle PCO equals angle ACP plus angle CAP. Realize that these two cancel, so angle PCO is equals to angle CAP. What does that mean? Angle PCO is equals to angle CAP. So this actually just is very reminiscent of something very basic thing here. Property of circles, right? So if you have a tangent here, tangent here, this angle, let's call it alpha, will be equals to this angle, right? Now let me just highlight it out better. We're just saying, we're considering this setup and here. So they're saying that this angle PCO is equals to angle CAP. Isn't it very, very, very super similar to this? And it is, yeah. So we can now conclude that CO is tangent to green circle, because CO being tangent to the green circle is the only way to make this happen, where this line has to be tangent. Okay, so we can pull a similarly. Can just do that for the red circle, and we'll conclude that OB is tangent. OB is tangent to red circle. Okay. And note that OC equals OB. Note OC equals OB because O is the center of the blue one. This is just the radius of the blue one. This is the radius of the blue circle. So they're equal. So let's compare this thing. Okay. Power of point O with respect to green. What is it? It's just OC squared. Now, power of point with respect to red. You know it's of O, okay? Is what? Just OB squared. Then since OC equals OB, OC squared will be equals to OB squared. So the power of point of O with respect to both the red and the green will be the same. Hence O lies on radical axis of XP extended. Hence O, P, and E are collinear. And we're done. So that is all for this question. If you have any questions, you can just email, and yeah, that's it.